Okay.
Welcome, everybody. My name is Jeff Remington from the Center for Science in the Schools at the Penn State College of Education. We would like to welcome you to Penn State's AI Week, which is from April 1st to April 5th. As you see on the screen, you can connect with us to find out more about that information. You can find out more about what we do at the Center for Science in the Schools at the first link there, csats.psu.edu. We at CSATS translate Penn State researchers' work into K-12 learning experiences. Second link on that screen is the AI Hub, which is the one-stop shop for anything AI at Penn State. So I'd encourage you to look at the AI Hub when you get a chance. All sorts of great resources to connect with and research projects and services to connect with as well. And then our last link down there is for Penn State Outreach. And if you would go on the Penn State Outreach site, you can see lots of connections to K-12 and great experiences. We are having some minor technical difficulties. We're trying to get the chat enabled so you can introduce yourself in the chat in your role. We will have a question and answer session and a capability for you. So if you have questions during the webinar, you can just put them in that chat, in the Q&A chat. We will have concurrent sessions going today from 10:30 until 1:30, and we'll just have transition slides in between sessions so you can go from there. So without further ado, I would like to introduce Steve Erfle. He is the author of Electronic String Art, Rhythmic Mathematics, Taylor and Francis 20 Intermediate, Microeconomics, and many, many other things. You can find his presenter bio on that QR code on the screen. And he has a great session for us for the next hour, and he'll be taking some Q&A as well towards the end. And Steve, without further ado, I'm going to stop sharing my screen and let you share your screen and take it from there.
Okay. So can you guys see the Playing with Polygons screen?
Yes.
Okay. Let me just start off by trying to explain a little bit about my background. I'm not a person who is steeped in AI or even in mathematics for that matter. I'm an economist by training, but I was fascinated as a kid by string art and the idea that you could create curves from straight lines. And so I did a lot of that when I was a kid, and then I kind of put it away for the rest of my life until my kids were in grade school. And one of their teachers asked me to show them some things at the end of the year that you could do with Excel. And I figured out that I could recreate the string art that I had done as a kid electronically that way. All this stuff is sitting in the background area here of the homepage. I ended up writing a paper on this in 2020 at Bridges. We were supposed to give it in August of 2020 in Helsinki, Finland, my daughter and I. Unfortunately, it had to go virtual because of the pandemic. And then my other daughter wanted to do lower end things. And so I did something with her and a couple of other friends of hers just on polygons and stars. And as a result of that, I kind of came to the realization that if I restricted my focus to polygons and stars, then I would be able to really do quite a bit more, and in particular reached out to people who are much lower down the food chain. In other words, I've shown this stuff to kindergartners, and they eat it up. They don't exactly know what they're seeing, but that's all right. They're still immersing themselves into it, and as they immerse themselves into it, they start to see patterns, and pattern recognition is what mathematics is all about. And what I'm trying to do is to teach kids to be excited about math rather than dislike it. So you can read about my, underlying philosophy here, and this would have just stuck with me. I started writing this in 2021. This blog called Playing with Polygons, and after about a month, I Googled myself, and of course, I didn't show up because nobody knew that I was doing any of this. But there was this guy in the UK, happily, who used exactly the same words. And during the first month of the pandemic, he did this. And so I connected with him on LinkedIn. Luckily, I was able to figure out who he was, and he wrote back to me, and we quickly became friends and colleagues. And he, in short order, created a web version of what I had done previously strictly as Excel materials. And so this is that web version, and you can use it to teach simple mathematics. And I will say that I've only in the last 3 weeks or so been gifted by him. I originally had only the one homepage, but then about a year ago, or I guess 2 years ago at this point, I did spirals and did that as a bridges piece in 2021. And he made a web version of that as well for me. So you can kind of look at both of those. But only a couple of weeks ago did he come up with this new version. And this new version is something which, had I known about it, the book would have been quite different. The book I'm talking about is Electronic String Art, which I guess you can get to through that there. But this is just a sequence player, and so what it does is it, given a set of parameters, it will, and you can show it up, slow it up, or speed it up or slow it down. It will run through all of the full density images, in this case 492 lines, but it's based upon, this is a 12-5 star, 12 gone 5. So I oftentimes will stick with starting with 12 pointed images, because to the extent that kids have some familiarity with numbers larger than triangles or squares, 12 is very common because of clocks. So what you can do, what I would do, I haven't written this up yet, but if I were teaching this in the lower grades, I would just put this on the screen and then start talking to kids as we get into the notion of commonality by saying something like, well, that's with a jump of 5. So it's going for, you can see, down to here. But what if we jump 4? Well, jumping 4 leads us to, whoa, a triangle. Well, why is a triangle? Well, because 1, 2, and 3 are ignored, and 5, 6, and 7 are ignored, and 9, 10, 11 are ignored, because the only thing that matters is 4, 8, and 12. Well, what happens if the jump's 3? Well, now it's a square. What happens if it's 2? So you can have interesting discussion even before they know about multiplication on just images. So you say something like, well, it's half as many here, but what about 13? Well, 13 gives you a star, but what about 14? Well, now you're back to a 7 gone, and you can go even further and say 15. Well, now it's a 15 2-star, but what if we make it 3? Well, now we have a pentagon, and you can keep playing with these discussions, and the kids are mesmerized, I think, by the fact that those are just pretty beautiful images that are happening in the background, even as we're talking about some fairly basic stuff. So this is a new direction for me, because I've only been with the sequence player for a very short period of time. The entire book was written based upon this much simpler version um, here. And that what I'd like to do is to spend just a little bit of time talking about how the images work. And so I'm going to go and bring up. I'll show you where the files are, but I've downloaded them so they don't take time. I'm opening the String Art for Teachers file right here, and I'm just going to bring it up to my screen here. So this is once it gets full size, something which you can use depending on the grade level. You might want to show equations and show information or not. So I had that kind of hidden. But I'm going to leave it open for you since you're teachers generally. But here's what I would do. I would first of all start by just talking to them about vertices. Well, vertices are, we have a foregone. If we have 3, it's a triangle, and we can just change this to whatever number we want, right? And as we change it, we get closer and closer to a circle. I'm going to turn the circle off. But you could talk about it with the image on or with the image off, and you can talk about it with labels. So this is set up very much to be able to be done in class. And then if you want to talk about jumps, well, what are jumps? Jumps are simply, instead of going to the first line, let me just set up lines so you can see where the first line goes and make this 1. So now it's a single line. So now we have a 11.2 star. What about 11.3 star, 11.4 star, 11.5 star? 11.6 star turns out to be the same as 11.5 stars, except it's just drawn counterclockwise. And the reason for that is 6 is larger than n over 2. So if we go back here to, let's just take this real quickly back to 2 and think about what it means to have subdivisions. That's the next thing. So let's talk about subdivisions. Subdivisions are the points that are simply between, I'm going to make this 1 so you can see first line. And I'll make large subdivision dots so you can see it. If we don't have an image at all, then as we increase subdivisions, it just means we have more and more lines on this vertex frame. The vertex frame is the 11.2 star. These dots are the points that will be used as endpoints for the final image. So we can make this any number we want. I'm going to restrict this back down to, let's say, 3, and then talk about how the counting rule creates the image. So here's the counting rule, is P, number of points you count before you draw a line. So you draw 2, and if you draw the second line, it's going to go from here to down here, and the third line here, and the fourth line here, and then the 5th line, and so on. And that's how this image gets created. And as we walk through, we get different kinds of images just based upon walking along this 11.3, 11.2 star. So you can see that the image in the end, let's turn off vertex frame since it's a little hard to see, and subdivision points, and you will see that what we have is just this kind of fat, puffy 11-point star. And if we change from 16 to 17, the only thing that happens is we draw in the other direction, and that's because 16 plus 17 is 33. And so that's the basis of string art, is just drawing images based upon playing with these numbers and just seeing what happens. Now, out of that, a lot of fun things can occur, and it gets at a lot of different mathematical ideas, but in a very indirect fashion. So I guess my thought is, and what I want to have happen for students is for them to find something they like and then dig in and try to understand it a little bit more. So the string art chapter, all of this material here in this images with subdivisions is part of the electronic string art book, which just came out in February. But the nice thing that Taylor and Francis did is they allowed me to keep this website. So this is freely available for people, and you can get to all of these. The way I've written this is, instead of writing it like a regular book where you read from front to back, the idea here is to find an image you like. Here are some examples of things you might like. And if you say, I want to learn about porcupine polygons, well, here's a porcupine pentagon, and we could see how it's drawn. And we could do that just by doing this. And the interesting thing that I think students find kind of fascinating is the fact that this internal image, which is quite clearly curved, is not because there are curves there. It's because it's done with straight lines. This is all part of string art. And so what happens if we change jumps from 1 to 2? Then we end up with a porcupine star. I'll show you right now. It looks like that. What happened, the reason that vertical line is sitting there is because it was going between images, and you have to just let it kind of, Liam's version, clear itself out before you start see a clean image. This can be sped up or slowed down, and this can be played with ad nauseum. So you end up with quite a few interesting things that you can talk about up and down the K-12 curriculum. Things as simple as counting rules, right? So skip counting. But it really it digs in here in commonality when we talk about the number of lines in the image and greatest common divisor, those kinds of issues, or sub-images, cycles. So let me head back to this image and just show you another one to give you an idea of something that can be done with at a higher end of mathematical exposition. This is an image that took me a while to actually understand, but I'm going to put it on pause and show you the first 7 lines here by doing this. Take this up to 7. And you can see there are kind of 3 triangles here. And I call this 3 shape-shifting triangles because if you watch this occur, what happens is, let's just look at the subdivision dots. These are the subdivision dots, and notice that the 7th line ends up 1 past the top. Well, that's because 163 times 7 turns out to be 1141. And 30 times 19 is 570, and 570 and 570 is 1140. And so this is 1 past the center. This is a notion from modular arithmetic called modular multiplicative inverses. So it's like the notion of a multiplicative inverse, except that it's done with modular terms. So you could spend quite a bit of time talking about that, but watch what happens here. What's going to happen is after 7 lines, you're here, after 14, you're here, and 21 and so on. It's like walking. I call it a single step image. So I'm going to play it. And it's a little bit busy with those subdivision lines in, so I'm going to turn those off, and the next time it'll come up, it'll be clean. But this image took me a while to understand, and I had to go back and learn my group theory and start thinking about some stuff I hadn't thought about since college. But once I noticed the nature of the beast, I noticed that that calculation did not involve anything about jumps. So the interesting thing is if I make this change, I'm going to change to a completely different one when it gets to the top here. Let you see 7. You can see it moves pretty quickly, but it clears itself out. And so you'll see a clean image of this. This is exactly the same thing. It's moving around and it's modular multiplicative inverse. And it works for any jump level. So there are 14 different distinct images using this notion. Modular multiplicative inverses are clearly not something that's talked about in K-12 as a traditional rule, but what I've done is I've written some mathematical stuff here, very simple primes and composites, talking about commonality, talking about Euclid's algorithm. The interesting thing is Euclid's algorithm turned backwards. If you back up Euclid's algorithm, you can actually find modular multiplicative inverses, and I talk about that down here. So these are, again, 1 to 2 page documents, each one of these. They're part of the book itself, but they are also part of just what I've got sitting on the website. I've created a few electronic videos here, the single step images. This gets at the edge of modular multiplicative inverses, but these first 4 videos are another way in. And I created these about a month ago, you can see, because I had this idea when I was at the Generative Art Conference in Rome of trying to create some basic videos that some of the other presenters said, why don't you do some of these things in video form and explain some of the material in video rather than on paper. And so that's what I've done here. And what I want to do is I have colleagues. Dickinson is luckily a place that really, really has lots of international students. And so my idea for the future has, this is still very new, is to create videos in different languages. And then we can take this to people in Mexico or in Nepal or wherever, Vietnam, and show them to people. Well, that's there's a ton more in string art that I could show you, but this at least gets you started. I guess I should probably mention the double jump thing. Let me do that by bringing this in that I was one. This is a 4 jump model, but this guy is a double jump model. So what it means by double jumps is we've got a 20-foregone here, and we go 1 forward and then 21. And so that's like going back to 11 o'clock and 11:30 back to 10 o'clock. And so that's how this vertex frame is created. Now, the cool thing that you can do with double jumps and stuff like that is get some really interesting things happening. And it's much more complex, but of course that's you got to run before you, or walk before you run. But I'll show you what this looks like with using Liam's thing. I think of this as kind of a beating heart or beating clock, because it's a 12, there are 12 gods, but there are 2 of them fighting with each other. This is a 1200 line image, a set of images that's that what you just saw going all into the center. That was the porcupine. And so we're almost close to finished up here, 1200 lines. This one here, this other version, I came across just as the nice thing here is one of the ideas in basic string art is that you end up not being able to do 6-2 stars because you either on evens or odds because it's continuously drawn. But if you use double jumps, you can get there, or multiple jumps. And here has lots and lots of 6-2 stars. And it has some very fun looking things that happen because of the swirl patterns. It creates swirls that are going in both directions. So that's just kind of a fun set of images. I have started to write some of this material into that one in particular, post ESA string art. This intertwined 6-2 star, this is exactly an explainer for what we just were looking at, that I posted about a week ago. One other thing about if you are trying to get older kids, let's say beyond fifth grade, a little beyond fifth grade, interested, you might consider doing something like this and having them do their own initials. So you can do things like that. Now, this is a little more work, obviously, and this is not obviously done in a polygon, but this is based on the stuff that Kate and I did in the Bridges 2020 piece, which predates the playing with polygons. But what I've found is that people tend to get excited when they can do their own initials. We can see another example of initials. I did one for generative arts, and so I have that posted here. This is just if you want to get a quick way in, this is a 10-page paper, short pages, which really pretty quickly brings you through a lot of this stuff. But the thing I wanted to show you in the end is that right there, which is another example of the only thing you have to do is you have to connect them. So I guess instead of having things all at the end, I would like to pause for a second and see if there are questions on string art, because I've got two other sets of things really to talk about. Counting issues, and maybe three things: spirals and cardioids. This stacked stars was just a way that I was teaching Liam what I meant by jump sets. So are there questions? By the way, let me just point this out then, since this is for teachers, here's my open invitation to teachers. It's on the For Teachers tab right underneath the homepage. And what I'm saying here is, guys, I'm an economist. I do this on the side just because I love it. But I've talked to the people at Mathematics Teacher, I've talked to people at Journal of Math Circles. They think that these things might be worth road testing. And if anybody wants to, I'd be happy to co-author something with people. So are there questions?
Feel free to put your questions either in the chat, since that's now enabled, or in the Q&A.
Well, they could also just ask a question. I mean, I can stop for a minute and somebody can speak up if they're interested.
Yeah, I'm not sure if I have the setting that their microphones are muted.
Ah, okay. I understand that.
Yeah.
So should I just keep going and then hold the questions till later?
Yeah, I think we can do that. That sounds
Okay.
good.
Let's do that. So what I'd like to do here is this whole set of material, these counting exercises, come out of some images that were in the double jump model that I just happened to show my mentor from UC Davis days, who said, "Hey, Steve, these are kind of fun. We can do something with that." And this is the simplest version. Okay, we have a more comprehensive version that is in September 23 of College Math Journal. It's called Up the Hill and Down Again. But I have that open right here, so I'll show it to you. So this is the landing page. And this is meant for, I've done this as low as fourth grade. I've been in classrooms where I've talked to fourth graders and went through it with them. So I'm going to spend about 5 minutes and do that here. If you ask kids how many dots there are, they can quickly come up with the answer. Well, there are 100 because it's 10 by 10. And as soon as you know multiplication, perfect squares are kind of the thing you gravitate toward. If you ask how many triangles there are here, that's a much harder question. This is a 21 gon that is set up with a sharpest triangle that looks like that. Okay, so you go just before halfway and then just after halfway, and you make this triangle. Then if you back up one in each direction for the horizontals, you get a bunch of horizontal lines. And if you back up or go the other direction, the other two directions, you get a bunch of parallel lines. So you end up with 3 sets of parallel lines that create an image that looks like this. The question now becomes, how many triangles are there? Well, what I want to do is to think about this biggest triangle, the one that we originally started with. It has a base at 1, it has a base at 2, it has a base at 3. In fact, it has a base all the way down to 10. So there are 10 of those. If we go to vertex 1 or vertex 20, quite obviously what's going to happen is we're going to drop two numbers because we don't have this base or we don't have that base when we're over here or over here. So it goes like that. And so if you show this to kids in 4th grade, they'll say, okay, I can do this. 10 plus 8 plus 6, and they start counting around. And then I say, wait, there's a better way. Here's the better way. Instead of thinking of the square as a length and width, think of it by diagonals, and think about these as marbles. And think of those diagonals as kind of racetracks, and let the marbles roll down to the bottom. You'll end up with 1, 2, 3, up to 10, and then back down to 1. You have a visual proof right here of the sum of the numbers from 1 to 10 and back to 1 is equal to 10 squared. Now, it's a formula that all mathematicians know, but not a lot of non-mathematicians know it. And it's a pretty fascinating formula, and that works for any. So you just take that main diagonal and you reduce, square it, and that's what you've got. How does that relate to the triangles? Well, instead of going around, why don't you go zigzag? 0, 1, 2, 3, up to 10, back to 1. They're exactly 100 triangles. And if I change this, now there are 81. Now, most 4th graders think that's pretty cool. So I would, and even older than that. I was doing this in a high school geometry classroom about a year ago with Jeff Schwartz at South Middleton, and he said to me, Steve, there's another pattern here, and he said, let's look at triangles and trapezoids. Right. And so if we think about smallest triangles and trapezoids, I'm going to think about it kind of horizontally along these. There's 1 here. There are 1, 2, 3, 4, 5 here. You can see that at the bottom there are 3. It goes like this. It goes up by 4, goes down by 4, or up by 4 from the bottom. Anyway, all of these are little prompts that you can use for going in class and talking through, plus the tables give you the same information in tabular form. So how does that work? Do we add all of these numbers? Well, let's look at squares in a slightly different fashion. We're going to look at them this way. Go from 1 to 2, 3. What's being added? Well, this L-shaped thing is being added, right? And the L is just 10 by 10, but you can't count that diagonal one twice. And so it's 19. But guess what? That means we are adding an odd number each time. And so what you can see off to the right-hand side here is that the sum of the first 10 odd numbers is also a perfect square. So if we go back to this image, the sum of these numbers, if you notice, going from top to bottom, back and forth, It's the first 10 odd numbers. In other words, they're exactly 100 smallest size triangles and trapezoids as well, a separate idea. And if we change, then it's the same idea. What's happening, the easiest way to explain this to kids is this way. Start with this, then ask what happens next. When we move to 5, you get a tighter angle, but you then just change the ending wave. It just goes back and forth wave-wise. But notice the top and the bottom don't change. So this 1, 3, 5, 7. Next one's going to have 1, 3, 5, 7. The only difference is now there's going to be a downward one that's a 9. And so that pattern, again, pattern recognition is mathematics understanding, is exactly another version of alternative versions of perfect squares, which is why we had our original paper called Alternative Vision of Perfect Squares. We had only this one vision, and then Jeff said, hey, there's another vision. And we had the Gnomons thing done. And by the way, here in the diagonals, if you want to talk about Gaussian addition, there's stuff on Gaussian addition here down at the bottom that can help you show people that not some of the numbers from 1 to 100 is 5,050, for example, right? You can work through all of that stuff. So that is the second, the simplest counting exercise. Different things happen when you have even polygons and you want to do sharpest even polygons. Turns out you can no longer get isosceles, but what you can get is you get right angles. And there are two versions of it, and they both lead to another nice conclusion. And then you can go to different sharpest even ones and isosceles. This is actually where I started with Don. But this is a little more complex because it includes internal apexes. On the other hand, there's a general version here, which is tremendously open-ended. I'm just going to open it and show you it quickly. It is right here. And this basically runs off of 5 numbers. They're in yellow. They're also labeled, so you can write them as equations. But this is set up right now to do a bunch of equilateral triangles. On the other hand, if we wanted to set it up like we just had it, what you could do is you could do the following. You could say equals integer of t n over 2. And what this is going to do is going to give you either exactly the number, and then what I'm going to do next, I'm going to just say this plus 1. And that gets me those sharpest right triangles. But the version that you guys were looking at before that I explained to you is exactly this image. And so this alternates between sharpest right and sharpest non. I'm not saying that you want to show them something like this, but guess what? What you could do is you could say the following. Let's play this game. Let's just stop this at 7. And let's ask the question, what happens after we continue increasing? Well, this is an image that, you know, there's 1, 2, 3, 4, it goes up to 7, then it's going to count 7 for a while, and then it's going to go back off 6, 5, 4, 3, 2, 1. So you are just going to have to work out what the formula is for any given n, but you can count the number of triangles here, and it would be a great group exercise for a intermediate level class. You can read about that stuff a little bit. I have not written papers or explainers on it, so this is kind of in the old style. You know, I was writing some before I got to the idea of doing explainers. Let me talk a little bit about subdivisions or spirals. This is based upon a Bridges 2021 workshop that I did. It was also virtual. Unfortunately, I still was trying to get to Helsinki, but I did have written a few explainers on here. I have others that I know that I want to write. I have not gotten them there yet, but let me show you that basic. I think it's right here, spirals. So this, in terms of intellectual material, is probably kind of the easiest thing after polygons and stars. It's easier than string art because it's based upon just 3 numbers. And the idea is very simple. This looks like a nice Archimedean spiral, and it is based on the following idea. If we have a parent polygon, we are simply going to go in 1/r each time we draw a line. So this is 1/200th in, 2 200ths, 3 200ths, and so on. Once we go around the 50gon, we've gone in 50 200ths or 1/4, 2, 3. That's why there are 4 rounds. But what if we change our jumps from 1 to 2? We can. This actually is linear. It doesn't look it. It looks awfully smooth. But when you start increasing this, now it starts looking, less smooth, but you get some very pretty things happening like this. Why is that decagon there? Well, the decagon is there because we're jumping 5 vertices. We got 50 total, so we get a decagon. How can we make that twirl? What if we change this to 49? Well, then the 50th is right over here. What if we want it to twirl in the other direction? Well, let's make it 51. So we get these the ability to make these very pretty swirls. And let's keep going. So why is there such a nice 7-gon swirl here? Well, quite obviously, 7 times 7 is 49. So we end up right here. That's why we're having this kind of counterclockwise to the inside swirl. If you can keep this up, you'll find lots of fun different images. And you can ask questions as you go along. Start at the 5 and say to them, how do you make that in twirl a little bit? Well, again, 49 or 51 will do it. And there are 2 different versions of mirror images. One is this version that I do, which is just X and Y, and it'll allow you to find some very, very pretty flower style images. Liam's got a different version, kind of interesting. Let's head back here to polygons, grab any one of them and hit spirals. And if we ramp this up to 200, jumps. I'll make this 50. This is exactly the same, right, that I was doing. But Liam has this version where he just keeps wandering through, pushing through. And so his spiral does not end at the top, but ends off, in this case, right here. But if you do different values, there are fun ways of trying to figure out what's going on between the 2 of ours. And I haven't written the explainer on that yet, but it's doable. And then cardioids. Cardioids are just fun stuff. And I'm going to show you this cardioids with loop file since I still have a bit of time. Well, here's the basic cardioids file. What cardioids are is even simpler in some ways because it's based upon just 2 numbers, N and K. And K is, think about the vertices from 1 to 360. You take any vertex I and you multiply times 2, and then you draw a line between those 2. And if you do that, you will end up with this upside down heart, right? But what if we change K to 3? Well, it turns out that you now have 2 of these cusps. And in general, you have one less. So there's going to be 6 cusps here when it's 7. When I started playing with this, I initially found, it gets pretty busy. There are pretty images like these sub cusps and large cusp, but there's still a lot of lines going on there. 359 lines in general, one less than n, because you don't get a line at the top. It maps to itself. But what I was surprised by initially is the following. I'm going to take this all the way out to where I show you my surprise there. And I said to myself, why is it possibly the case? I'm losing some of my screen. Why is it possibly the case that it has half as many lines? Well, it turns out that the answer is really quite a nice little piece of mathematics. 19 times 19 is 361. And so think about where 1 maps to. 1 maps to 19, but 19 maps to 361, which is 360 plus 1. So every mapping, these are paired vertices. They map back and forth to each other rather than having 2 lines. Much easier to show this for a smaller number like 10. So if we do this with 10 and we do this with, I think my number's here, yeah, 99. For numbers of vertices less than 100, I allow the numbers, but you can do it now. Watch, 1 to 10, 10 goes to 100, but 100 is 99 plus 1. 2 goes to 20, but where does 20 go? 20 goes to 200, which is 99 plus 99 plus 2, and so on. So that is talked about down here. I do have a fair number of explainers for this. Not nearly as many as the string art, but stuff there. There are some interesting aspects of this that are pretty fascinating, because these lines are drawn one at a time, but they create loops. For example, if you have just following through what I've done, this vertical line here goes 2, 4, 8, blah, 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 and I draw all the lines. Notice, with the exception of just a very few number of lines, everything is done in this one loop. Well, guess what? The other lines come in this second loop. So it's kind of fun. That is what I've got at this point.
And Steve, we have 2 great questions for you.
Yeah.
One comes from Than Lee. Is there equations associated with these polygons, the polygon designs?
There are certainly equations, that are associated with them, but to me, that's not something that I would necessarily want to push on students, because it would intimidate most people. What I've done is, it's all done with sine, cosine. It's all done with trig. But I don't want to force that on students. On the other hand, go to cardioids, for example. There's 3 special cases. This is called a circle fan. Okay, I'm calling it a circle fan. And this I had actually asked Shakarian, stupidly, because I don't know my trig that much anymore, other than what I needed to know to build the vertices. What I said is, can we talk about the lengths of these things? It turns out it's very simple to come up with equations for the lengths of the various spines in a circle fan. And that's of use in if we are trying to do something like a mystic rose. A mystic rose is an image where every vertex is connected with every other vertex. And so you end up with this layering of different length chords. And you also end up with these kind of circles of implied inner circles. And both of these I haven't written it yet, but I know what the answer is in terms of what are the distances involving just n and j. Um, so yes, there are equations, and if you want to get at some of those, there are certainly parts of this that are amenable to that. In the electronic string art book, let me just quickly go there. In the book, one of the nice things about it is they have this preview, which gives you a table of contents. Okay. And so we've wandered around quite a bit with this, but what I'm trying to get to is this idea, challenge questions. So there are lots and lots of questions that can be asked and described at different levels. There are challenge questions down here for the double jump models and all kinds of other things. But this lays out the basic structure that I was showing you before. It's just a little, it's more effectively done. Suggestions for teachers. There in an entire version here. By the way, that reminds me that I need to show you these introductory web guides, because I wrote a set of explainers, one-page documents, 3 of them here, that are that don't use the word multiplication or division or anything like that, but simply talk about how to understand the basic images by just changing the numbers N, S, P, and then J is then in the second explainer. But getting at the idea of greatest common divisor without talking about greatest common divisor, talking about how many lines there are and what you're seeing. So these, here's J. And then the other one gets at various drawing modes. This is all based upon Liam's initial version, does not have anything to do with that one that I was showing you that kind of jumps out at you. It doesn't do. I've only had that one for a month. Questions?
Great. And the other question comes in is, can we use this to teach proof by induction?
Absolutely. Yes. Yes. In fact, I mean, so a lot of that is very, very much the strategy that was taken for some of the counting exercises. This entire counting area, you could do by a proof by induction very easily. Again, I'm not setting it up for that because my goal here is to catch kids before they have to learn those more formal things, catch them when they're being turned off by mathematics in the lower grades. It's oftentimes taught by teachers who really don't want to teach mathematics, right? And if you can give them some tools that they can say, hey, here are some basic things, not just play. Show me the image you like the best. You know, show me, let's look at, you know, this is my drawing Moses, this star, how does this thing work? Well, it's using only 1/10 of its vertices of the subdivisions, but it's a very pretty image when you just get it, watch it happen. And what I want kids to do is to find some joy in mathematics rather than feel that they have to go through the formality. I'm not saying I haven't, my undergraduate degree is mathematics. I do believe in proofs, but that's not the basis of where I'm at here. What I'm really thinking about is this is very much tied, although I didn't know it at the time, when I started doing this. It's just my gut feeling, but there's a guy also from UC Davis named Sherman Stein who wrote an article called The Triax: Explore, Extract, Explain. And what he suggests is the best way to learn mathematics is to explore, gather data and explore from that data, extract a pattern, and then try to explain that pattern. So his strategy is very much in line with mine of let it play. That makes sense?
Yes, it does.
Okay. I mean, I'm not saying that I'm anti formal proof. I'm just saying this provides a tremendous amount of visual support for some things you might want to be teaching anyway. For example, kids will often look and say, "Why do I care about greatest common divisor?" Well, my gosh, you can see that in spades by just doing a very basic, um, go to the simple, the starting point, not this one, but the starting point that Liam's, when nothing else, this is his starting point, and that has, well, why are there only 8 lines if there are so many subdivisions? Well, it's because we only count in sixths here. But if we make this 29, now we've got a lot more. And if we go 28, well, now it's 1 and 4, 1 and 3, 1 and 2, every one. So this can be used to very quickly talk about the practicality of greatest common divisor, right? Commonality. And we'll give them something to hang their hat on that is that's tangible.
Thank you so much, Steve. We're going to have to transition and get ready for our next session. If you would please put your contact information in the chat if you're comfortable, so that people can connect with you.
I can do that, but I can also say the following. If you go to a number of places, but at earthly@dickinson.edu. It's also, if you just go to the homepage, it's the bottom of the homepage, and it just says site by earthly@dickinson.edu. Okay.
Wonderful.
And if you Google playing with polygons, it'll either be the first or the second thing that comes up, and Liam's is the other one. So does that help?
Yes. Yep.
I think I filled that hour okay.
Yeah. No, that was great.
All right.
That was great.
Thanks, Jeff.
Thank you very much. That was amazing. That was amazing. Okay, we have a few minutes to transition into our next speaker. But if you have a camera handy, your cell phone handy, you could do this Slido, and in one word, for the participants, for anybody that's on the call, let's see how you feel about artificial intelligence in one word. Give you a couple minutes to do that. Just take your phone, put it up at that QR code, and you're going to be able to just pop right in there in one word. How you feeling about artificial intelligence? We've been steeped in generative AI for the past year. Let's see how people are feeling. And again, we'll soon transition into our next speaker in a couple of minutes, but let's just see how people are feeling. We are definitely getting some interesting descriptions up there. For the most part, positive. Okay, we are just about ready to start our next presentation, and I'm going to turn it over to my colleague Greta Kellogg, who will be hosting this along with Merdad. Greta is the assistant director for Amy. So I'll let her introduce herself and then I'll let her introduce Merdad.
Good morning. It is a pleasure to be here. I am working with the Institute for Computational Data Sciences at Penn State, and we are always thrilled to work together with CSATs and with Jeff Remington and Amanda Smith. And Amanda's going to continue looking for Q&A. Dr. Madadi is joining us this morning, which is a delight. He is Dorothy Quiggle Career Development Assistant Professor of Computer Science and Engineering, and has a very personal interest in teaching K through 12 and as an expert in artificial intelligence. I'm sure you will get a lot out of his conversations this morning. Please do not hesitate to put in questions and comments in the Q&A, and we will